Hello and welcome to problem set number 11. Our topic today is intermolecular forces of attraction and heating curves. Before we get started, I do want to remind you quickly that the worksheet to accompany this problem set is available online through my website, and I do highly recommend that you have that in front of you as we go through this video. All right, with that said, let's get started with number 1. Ethanol molecules, and I've given the formula there, are capable of hydrogen bonding to one another, but dimethyl ether molecules, and again I've given the formula, are not. Given this information, complete A through D below. A, draw a Lewis structure for each molecule. Okay, so number 1A, we're going to draw a Lewis structure for ethanol, and I gave this formula already in the worksheet. I'm going to draw a Lewis structure for dimethyl ether, and I gave this formula in the worksheet as well. Okay, so the good news here is that I've shown the order of connectivity in the formulas that I gave you. So we know that hydrogen must be terminal, so this carbon has 3 hydrogens attached to it in the terminal positions, and then that carbon is attached to another carbon which has only 2 hydrogens, also have to be terminal. Next comes an oxygen and a hydrogen, and now I'm going to complete my octet on my oxygen atom. Everything else is satisfied with octet already, so my Lewis structure looks like so for ethanol. And for dimethyl ether, same thing. We have a carbon with 3 hydrogen, and we know that hydrogen have to be terminal. Then comes an oxygen and another carbon bound to 3 hydrogen. I'm going to complete my octet here on the oxygen. Okay, so part A is done. B, use your drawings from part A to explain why only ethanol can form hydrogen bonds. Okay, so B, let's do B in a different color here. Do B in blue. Okay. All right, so what I want to do first is go ahead and redraw these 2 molecules and show the molecular geometry about the oxygen atom. Okay, so in this case, we can see that we have 1, 2, 3, 4. We have 4 charge clouds about the oxygen atom, but 2 of those are from lone pair electrons. So although the electron pair geometry with 4 charge clouds is a tetrahedral, because 2 of those are lone pair electrons, the molecular geometry is going to be bent. So I'm going to go ahead and indicate that here. This is going to be a 109.5 degree bond angle. It's going to have a bent molecular geometry. Let's write geo for geometry. So I'm going to redraw that down here. And these are tetrahedrals, but I'm not too worried about those because I know that the hydrogen bonding is going to be happening over here. My partial positive and partial negative charge buildup is going to be building up around the oxygen and the things that is attached to the hydrogen in that first carbon. So that's why I focused really right here. All right, I'm going to do the same thing for the dimethyl ether. Okay, again, we've got 1, 2, 3, 4 charge clouds, 2 are lone pairs. So we're talking about a bent geometry about the oxygen atom. So a bond angle of 109.5, bent molecular geometry. All right, mole geo, just to save myself a little time. Okay, so oxygen, lone pairs, CH3 and a CH3. Okay, all right. So we're showing why this can hydrogen bond while this one cannot. All right, so remember what a hydrogen bond is. A hydrogen bond is a special type of a dipolar force of attraction where a hydrogen atom that is covalently bound to a highly electronegative atom such as oxygen, nitrogen, or fluorine is then strongly attracted to a highly electronegative atom of another molecule. Again, either oxygen, nitrogen, or fluorine. And so we can see here, and I'll go to the black pen here, we can see here that we have a hydrogen atom covalently bound to either oxygen, nitrogen, or fluorine. In this case, it is an oxygen. So that means that this hydrogen will be very partial positively charged because the electron density being shared here in this bond is going to be more strongly attracted toward the electronegative oxygen atom, which means that our oxygen is strongly partial negative in charge. Okay. So then we can imagine an attraction here between this extremely partial positively charged hydrogen. It would be attracting the partial negative portion of another ethanol molecule, which would happen to be the oxygen atom. Lone pair electrons on the oxygen atom. So I'm just drawing another ethanol molecule, and I'm showing that hydrogen bond. Let me circle that whole complex in green. Okay, so the hydrogen, which is very partial positive in charge because of the polar bond here, is covalently bound to an oxygen and then strongly attracting the oxygen of another ethanol molecule. So let's write for our answer here the explanation of why ethanol can hydrogen bond to another ethanol molecule is that ethanol has hydrogen covalently bound to an oxygen atom. Okay, that's why that hydrogen has a partial positive charge. So let's write, which makes that hydrogen partial positive. I'll write that delta plus, partial positively charged. That partial positive hydrogen attracts the partial negative oxygen of another ethanol via hydrogen bonding. I'll write H bonding. Okay. All right, so this explains why an ethanol molecule can hydrogen bond to another ethanol molecule. Let's take a look at the dimethyl ether and see if we can figure out why it is incapable of hydrogen bonding. Because a lot of students are going to look at this and they're going to say, I see hydrogen, I see oxygen. It should be able to hydrogen bond, right? Remember, the hydrogen has to be covalently bound to the oxygen. And in this case, none of the hydrogen are. We've got 6 hydrogen here, but they are all covalently bound to just carbon. And if you go back to your electronegativity chart and calculate the change in electronegativity for a carbon-hydrogen bond, you will find that it's 2.5 for carbon minus only 2.1 for hydrogen. That's only a change of 0.4. That's not even a polar bond. So these hydrogen atoms, not only are they not bound to an oxygen, they're not even partial positively charged because the carbon-hydrogen bond is a non-polar bond. Okay, so we've got hydrogen, but they're not covalently bound to either O, N, or F, and they are therefore not capable of participating in a hydrogen bond. So let's go ahead and write that over here. Okay. all 6 hydrogen in dimethyl ether are bound to carbon atoms. In order to have hydrogen bonding, we must have hydrogen covalently bound to O, N, or F. We don't have that in a dimethyl ether molecule. So let's go ahead and take a moment to see what type of intermolecular forces of attraction the dimethyl ether are capable of. We already know it's not hydrogen bonding because it was actually given in the problem. We just proved that those hydrogen cannot hydrogen bond. Okay, but if we calculate the delta En of an oxygen-carbon bond, we will see that it has a change in electron negativity of 1.0. It's 3.5 for oxygen, 2.5 for the carbon. So there is some partial positive, partial negative charge buildup in this molecule. The oxygen is partial negative and the carbons are partial positive. There is no partial positive, partial negative charge buildup on the hydrogens though, because remember, we already said that a carbon-hydrogen bond is nonpolar. Okay, it's only a delta En of 0.4. All right, now if this were a linear molecule, then those two forces would just cancel out and the molecule overall would be nonpolar, but it's not linear, it is bent. Bent because of these lone pairs here. Okay, so we do have a polar molecule. And therefore it is capable of London dispersion forces as well as dipolar forces, but not the special type of dipolar force known as a hydrogen bond. Okay, so it has London dispersion forces, all right, LDF, and dipolar forces of attraction, not hydrogen bonding. Okay. All right, so let's go ahead and erase all of this before we go on to part C. Okay, still number 1, but now part C. Draw 2 molecules of ethanol and show a hydrogen bond using a dotted line between them. We did that in part B already when we were explaining why it's capable of hydrogen bonding, but it's still good practice to do it again in every introductory chemistry class. This is something that your instructor will probably want you to be able to do. Draw a hydrogen bond between 2 molecules. Okay, so let's go ahead and do it again. So redraw the ethanol. I'll go ahead and give it that bent geometry there. Okay, and we know that the oxygen is the partial negative end, the hydrogen is partial positive. This would actually also be partial positive. I'll go ahead and draw it in there even though the carbon's not going to be hydrogen bonding, but it's still a good thing to get in the habit of doing, indicating all your partial positive, partial negative charge buildup. Okay, so I'll put my hydrogen bond, I'll indicate it with the green with a dashed line. So then the hydrogen, the partial positively charged hydrogen of one ethanol molecule is going to be strongly attracting the partial negative oxygen of another ethanol molecule. Okay, so let me indicate my charge buildup in this ethanol molecule. So we have partial negative, partial positive over here too. And then once again, I'll circle in green the whole complex, complex that is part of the hydrogen bonding. So remember, in hydrogen bonding, you must have a hydrogen atom covalently bound to O, N, or F. That's what creates that partial positive charge that's more extreme than what we would just get in a dipole-dipole force of attraction. Okay, so I'm going to circle all this. This is part of the complex. And then that partially positive hydrogen atom will strongly attract the partial negative O, N, or F of another molecule. Okay. So this whole complex is part of what makes up our hydrogen bond. And then the actual intermolecular force of attraction is right here. Okay. The attractive force between the two molecules. All right, let's go on to part D. Which substance, meaning either the ethanol or the dimethyl ether, which substance do you expect to have the higher boiling point? Okay, so both of these molecules are polar. So they both have the London dispersion force of attraction, because everything does, whether it's polar or nonpolar. But they also both have the partial positive and partial negative charge buildup in the molecule that makes them capable of the dipole-dipole force of attraction. It's just that the ethanol has an extreme, a special type of dipolar force known as the hydrogen bond, where that hydrogen is extremely partial positive in charge, and those electronegative oxygen, nitrogen, or fluorine are extreme partial negative in charge. And so that hydrogen bond is the extreme case of the dipole-dipole force. And so we would expect the molecule that is capable of the hydrogen bond to be the molecule with the higher boiling point. It's got the stronger intermolecular force of attraction holding those molecules together. And remember from our heating curve discussion, what happens when a substance boils is that you're ripping apart those intermolecular forces of attraction. So it's going to be easier to rip apart those weaker dipole-dipoles. It's going to be harder to rip, and it's going to take more heat energy to rip apart those hydrogen bonds. Okay, so the ethanol will have a higher boiling point. All right, BP for boiling point, because the hydrogen bonds are a stronger type of intermolecular force of attraction. So again, it's going to take more heat energy to rip apart those intermolecular forces of attraction that are stronger. Okay, that completes number 1. Let's erase here and go on to number 2. Okay, number 2, identify the intermolecular forces of attraction in each of the following substances. So I'm going to go ahead and write A through C up here. A is the diatomic molecule nitrogen. B is ammonia, NH3. And C is carbon tetrachloride. Okay, so first off, we know that all molecules have electron density that's in motion and that can temporarily be shoved to one side of a molecule or the other, creating instantaneous dipoles. So all molecules are capable of London dispersion forces of attraction. So I'm just going to go ahead and write London dispersion forces, LDF, for all of them. Okay. Now, if a molecule is nonpolar, then that's all it has, is those instantaneous dipoles, those London dispersion forces of attraction. But if a molecule is polar, then it also has permanent dipoles, and therefore it's capable of dipolar forces of attraction. And then if a molecule has a hydrogen covalently bound to either O, N, or F, then it's capable of a special type of dipolar force called the hydrogen bond. Okay, so let's keep that in mind as we go through these three problems. Well, nitrogen, that diatomic molecule, let's go ahead and use a blue pen here. That one's kind of easy, right? Because we know you can go through the 5 steps and draw out your Lewis structure. You should come up with a triple bond and then a lone pair of electron on each nitrogen there. So we know that the delta En, the change in electron negativity in a nitrogen-nitrogen bond, has to be 0, right? It's going to be nitrogen's electron negativity subtracting out nitrogen's electron negativity. It's going to be a delta En of 0. And that's always the case for the same 2 atoms that are sharing in a covalent bond. Okay, so we know that this is a non-polar molecule. Neither side is winning the tug of war for those 6 electrons that are shared in that triple bond. So the only type of force of attraction that can exist between nitrogen molecules are the London dispersion forces of attraction. So we're done with A. I'll put a little check here. We're done there. Let's go on to B. Okay. Ammonia. You can take a moment to draw your Lewis structure. Go through the 5 steps if you need the practice. I'm just going to do it fast because Lewis structures are not actually the focus of this particular problem set. Okay, so you should come up with a Lewis structure that looks like this. And we know that although we draw this bond angle as if it's 90, it's really not. This molecule would have 4 charge clouds, so the electron pair geometry that is tetrahedral, so these bond angles would be 109.5. And then because one of the charge clouds is a lone pair, we know that the molecular geometry, which just looks at the atoms that are actually covalently bound together and the shape that they take in the molecule, would be a little pyramid. So this has a pyramidal molecular geometry, so these are actually kind of angled down. Make that one come out and that one go in. Right, pyramidal here. Okay, and then if you calculated the delta En, you would find that the nitrogen-hydrogen bond is polar. You might have already known that because you know that a nitrogen covalently bound to a hydrogen is one of the requirements to create a hydrogen bond, to create that extreme partial positive and partial negative charge buildup. Okay, so nitrogen is your more electronegative atom, so I'm going to put my partial negative charge on nitrogen. All of my hydrogen are partial positive. Okay, and we can see that not only is this going to be a polar molecule, so therefore capable of dipolar forces of attraction. So I'm going to write that here. Whoops, go back to the blue pen. Polar, we write polar bonds. They are not equal and opposing, so they don't cancel out. So it's also a polar molecule. Okay, so I'm going to go ahead and write over here dipolar forces of attraction. Okay, so not only does it have those polar bonds, polar molecule, not only does it have the partial positive, partial negative charge buildup within the molecule, but it has hydrogen atoms covalently bound to the partial negative nitrogen atom. And so these hydrogen are all capable, let me go to the green here, of attracting the nitrogen lone pair electrons from another ammonia molecule and forming a hydrogen bond. You can also get the nitrogen attracting the hydrogen, partial positive hydrogen, of another ammonia molecule and forming a hydrogen bond. Okay, so let me just draw one hydrogen bond here. I'll just draw it to this hydrogen here, and let me pick a different color. Let's go to the blue. So we've got our lone pair electrons on our nitrogen of another ammonia molecule. Let's go ahead and show the geometry. So I'll do the wedged and dashed lines here. So let's circle it in a different color. Go to green. Here's our hydrogen bond. This is the actual intermolecular force of attraction here, but remember that the covalently bound hydrogen is also necessary to get the hydrogen bound. It has to be covalently bound to O, N, or F In this case, it's covalently bound to nitrogen. So I'm going to go back over here and I'm going to say not only does it have London dispersion forces, not only is it polar and therefore can have dipole-dipole forces of attraction, but it has the special type of dipole-dipole called the hydrogen bond. So ammonia molecules are capable of forming hydrogen bonds to one another. All right, last but not least, we've got our carbon tetrachloride. Let's go back to the blue pen and draw carbon tetrachloride. And again, if you need practice with your Lewis structures, slow down here, hit pause, go through your 5 steps, and make sure you come up with the same Lewis structure that I do. Great practice. Okay, all right, so then our molecular geometry would be a tetrahedral, same as the electron pair geometry, because there are no lone pairs about this carbon. So we know that this bond angle would not actually be 90, it would be 109.5. Make this one come out at you, out of the plane of the whiteboard toward you, and this one is going into the plane away from you, and the bond angle is 109.5. All of the bond angles are 109.5. Okay, tetrahedral molecular geometry. Let's write that here, tetrahedral. Okay, so it really doesn't even matter whether or not these bonds are polar or non-polar, because even if they're polar, they're going to be equal in magnitude, they're all carbon chlorine, and they're going to be opposite in direction. So no matter what, this molecule is going to be a non-polar molecule. Okay, which means that London dispersion forces are the only intermolecular forces of attraction that carbon tetrachloride molecules are capable of exhibiting with other carbon tetrachloride molecules. Okay, so let's go ahead and erase all of this and go on to our final problem, which is number 3. Okay, number 3. Ethanol has a melting point of negative 117 degrees Celsius and a boiling point of 78 degrees Celsius. Draw a heating curve for ethanol and label the line that represents the melting point, boiling point, and solid, liquid, and gaseous states. All right, so number 3, we are drawing a heating curve. So remember when we discussed heating curves in tutorial number 11, we said that they will always have the same general shape. That is, okay, we're plotting heat versus the temperature, and we're given the temperatures in degrees Celsius, so we'll go ahead and put those in degrees Celsius. The general shape will always be a line followed by a plateau representing the melting point of the substance. So I'm going to go ahead and label this as the negative 117 degrees Celsius, followed by another line representing the liquid state of the substance after it is melted, followed by another plateau, which always represents the boiling point of the substance. So in this case, because we're given the melting point and boiling point, I'm going to go ahead and write in the boiling point of the ethanol, the 78 degrees Celsius. Finally, one last line after that plateau to represent the gaseous state, the state at which the substance is in the gas phase. All right, so the first line is temperatures under the melting point. So this is the solid state. Let's write that in a different color though. Let's go ahead and put that in blue. So solid state, okay. So this is below the melting point. Okay. And then that first plateau, that is the melting point of the substance. I'll write MT for point because I don't have enough room there. Remember that at the melting point, the heat that's being added is all going into breaking apart intermolecular forces of attractions between the molecules, in this case the molecules of ethanol, so breaking apart some of the hydrogen bonds between those ethanol molecules so that those molecules are no longer locked in place, solid state, but now have flow. They're held less tightly and they can flow. It's in the liquid state above that temperature. So after the melting point, all the heat that's being added goes into increasing the temperature, the kinetic energy of those molecules until we reach the boiling point. That second plateau is the boiling point. And remember that once again, we see all that heat energy going into breaking apart all the remaining intermolecular forces of attractions that exist between those, in this case, ethanol molecules. So all that heat energy is going into ripping apart all remaining intermolecular forces of attractions. In this case, those are the hydrogen bonds between the ethanol molecules, because above the boiling point, the substance is in the gaseous phase. And remember, in the gaseous phase, there are negligible intermolecular forces of attractions between the molecules. Okay. All right, so we indicated melting point, boiling point, solid, liquid, and gas phase. So that is our heating curve for ethanol. So that will conclude our problem set number 11. I hope you will consider tuning in to tutorial number 12. Thank you.